we have started already discussing the properties, the low temperature properties of ferromagnets. Why I'm emphasizing the low temperature aspect of those properties, because we assume that the system, which is supposedly three-dimensional, the system of interacting spins, undergoes a transition into a spin-ordered state. And when we are below TC, moreover, we are well below TC. In fact, we are very, very low temperature, much smaller than the critical temperature, much smaller than the exchange coupling constant. So this is we're very close to the absolute zero. What we would like to know is what is the structure and the nature of elementary excitations. Because again, as before, we always follow Phil Anderson's idea that more is different. You can see more when you lower the temperature. If you are at high temperature, you cannot see more because it's a issue of statistical independence. And at high enough temperature, degrees of freedom, those degrees of freedom available in the systems are completely disentangled from each other. They fluctuate independently. And this is the famous equipartition of the energy and the independence of the specific heat on the temperatures. These are all of those things that reflect the simple fact that at high temperatures, different degrees of freedom don't talk to each other. They're completely independent. They are subject to fluctuations, but these fluctuations are so strong that any correlations, any dynamical or statistical correlations are out of the game. So therefore, what is at issue actually is under what conditions something new may appear. That is what Anderson formulated as more is different. You have to lower the temperature. You have to reinforce, if you wish, the correlations, the role of correlations in the system. And the correlations cover the large amounts of particles, and then new laws emerge, and new emergent features appear, and the elementary excitations involve many degrees of freedom, but qualitatively differ from what we have at high temperature. For instance, in case of phonons, instead of vibrations of individual atoms, we have waves propagating across the regions. The same will happen here now in the magnetic systems. Right? So if you take a magnet and bring it to a paramagnetic state by increasing the temperature well above Tc, the temperature will be so high that you will have a Curie law. You will have independent, uncorrelated spins in a given thermal bath. What do you know about that? You know that the magnetization and local magnetization follows the Curie law. I'm sorry. When this chi is inversely proportional, what is called the spin susceptibility is probably inversely proportional to T. In fact, in a three-dimensional case, it is basically 3 kb and with some coefficient proportional to S, either S squared or in quantum case it will be SS plus 1, something like this. This is the feature, this is the property of a completely isolated spin. Spin under the action of the heat, specific of the heat bath. But well above this is at T much greater than Tc. And well above, well below Tc. There is nothing like this. The spin becomes correlated. The spin becomes ordered, strongly ordered. And then you may ask yourself what happens when you try to excite, when you introduce excitations in such systems. Already that very temperature induces effects completely different. You may fluctuatingly imagine that you have basically all the spins up. Suppose that for simplicity your spin is 1/2 and the picture like this holds. So if all the spins look up and have their values 1/2, and at some point I overturn the spin and create a local spin excitation with delta SZ equal to 1/2 minus 1/2, it can be also get a 1. That's the change of the spin of the excitations, but this excitation, in the way I built it, is localized, which cannot be correct. Why? Because of translational invariance. You cannot localize a particle unless if there is a mechanism of propagation. This mechanism is driven by the quantum effects, which have been completely neglected when we were considering the ground state. In the ground state, the quantum effects do not matter at all. But here they do, because I can consider this pair, and because of the spin flip process, looking like S1 plus, S2 minus plus admission conjugate, I can transform this configuration into this configuration. And therefore the spin flip will move by one lattice spacing. And I can continue this process. And the spin flip will start propagating and transform to a quasi-particle. This is more or less what the spin wave is about. It's a local spin perturbation, or local spin excitations, being delocalized because of the overlap of the wave functions localized on the nearby lattice sites. And the overlap is just ensured by this quantum part of the exchange of time. This is this process. Because of this process, this spin flip starts moving. So this is the importance of the periodicity of variance. This is the way how a seemingly classical perturbation, excitation, just to overturn the spin, didn't do much, shows up its quantum nature, because if I keep the state like this and say nothing, it will stay for here forever. Also, only quantum effects enforce it to move. Spin flip process. Right? So we will be after things like this today. But we would like to do everything on a systematic basis, using a systematic approach. And that approach appeals to the large value of the speed. We have already emphasized that if the speed is much greater than 1, then quantum effects are small, are relatively small. How to see it? First and foremost, we will have to understand in which term we are going to discuss excitations. First of all, let me write down again the Hamiltonian. The Hamiltonian is minus J, absolute value. I emphasize that this quantity is negative. Summation goes over nearest neighbors, Sn dot Sm. The magnitude of the spin is large. And this I will rewrite as 1/2 J sum over N sum over G. I remind you that G takes values plus minus A1, plus minus A2. It would be also a plus minus A3 for a 3-dimensional lattice, but I can consider a d-dimensional hypercubic lattice. Particular cases are in 1-dimensional lattice, 2-dimensional lattice, 25-dimensional lattice. So we have not been able to deal with A. So the number of nearest neighbors is twice the space dimensionality, because each axis produces 2 neighbors for a given central speed. And here I write down Cn dot Cn plus G. I already said last time when I write down this 1/2, because each pair of nearest neighbors is accounted for once, only one time. To avoid double counting, I have to put 1/2 if I sum independently over all lattice sites and all nearest neighbors. Right? Okay. So therefore, this I can continue in the following fashion. It's 1/2 J some ng Sn z, Sn plus g z plus 1/2 Sn plus g minus Postgraduation conjugate. That's it. So you can assume that well below the transition temperature, you have a long-range order, and the long-range order can be described by this relation. The average value of the spin is non-zero and is given by the maximum value of the spin, which is the highest weight eigenfunction of the z projection of the spin, times the unit vector, which is not dependent on n, can be written like E naught. And now it's up to us to choose the quantization axis. Let us choose the direction of the spontaneous breakdown of the symmetry as the z direction. So therefore, what is written here, z, is just the direction along which we have ordering. Now I'm coming back to the case d is equal to 3. So it's 0, 0. It's a unit vector along the z direction. I can always call the direction of a spontaneous breakdown of the z-axis. In fact, I can proceed more consistently. I can switch on this weak magnetic field, which would polarize the spins, and then it will automatically fix the direction of the spontaneous breakdown. So now we have the notion of the ground state, which is the classical ground state, as you know already. This is the state when all projections of the z projections of the spin are take maximum values, S, and so forth, S. Which means that for any S and Z acting on the ground state, for any n, what you get is S at the ground state. Highest weight state. Always been looking up. Okay. And we also know that if we take this part and then consider separately this part acting on the ground state gives us 0. You cannot enforce any fluctuation, any quantum fluctuation organized by this term when acting on the state. This state is inert with respect to quantum effects. So therefore, you can immediately figure out what is the ground state of the system. The ground state of the system would be if I simply plug S number instead of each of this operator. That will give me minus 1/2 J, number of little sites, number of nearest neighbors, and S squared. You can rewrite this as, if you wish, minus J and D S squared. Now, if you were a very attentive student, I presume you are, you must have been surprised because of this S squared. In quantum mechanics, there is no such notion as S squared. In quantum mechanics, there is an operator, S square operator, which is Sx square operator, Y square operator, Z square operator. And its eigenvalue is not S squared, but it's S plus 1. Here instead, we have S squared. This is one of the manifestations. Quantum mechanics has nothing to do with the ground state. Because if it had, I would have the SS plus 1. When we calculate the quantum corrections to the ground state energy over antiferromagnetic, we will find out this is SS plus 1. All right? But not here. So this is the ground state energy. This is fine. like to consider excitations. We would like to take into account small deviations of the spin from the maximum value S. In other words, we would like to see the states with the local value of M being S minus M small. When M, okay, M must be positive in this case, but must be otherwise much less than S itself. That means that if I use this very well known picture of possible spin projections, this is the projection M equal to S, the highest weight state, and then I have states S minus 1, S minus 2, S minus 3. They are just going down, right? So I have to take into account the macroscopic, please don't forget, S is huge, it's a very large number. So in fact, this picture is very much resembles as a continuous semicircle, if you wish. So the step is so small, but it's quasi-continuous. So you can, in fact, play a game with sufficiently large M. M may be much greater than 1, but because S is even larger, sufficient to have M much smaller than S, but M itself may be very large. It may even reach the values of the order of the continuum length value, something like this, thermodynamically. But in any case, compared to S, deviations are small. It means that Sz for each atom is very close to its maximum value. And quantum effects are small. How to incorporate it into a description? This problem was resolved many, many years ago by two gentlemen whose names are Holstein and Primakov. It's a classic approach described in any textbook on magnetically ordered systems. The idea is as follows. Every time I produce a deviation of the Z projection of the spin by 1, so this is the ground state. Suppose I reduced the value of the Z projection of the spin by 1, it means that I create one boson. If I reduce it by 2, I have 2 bosons. And so forth, S minus K, I have K bosons. Every time I overturn a little bit by one step the Z projection of the spin, I give rise to a boson. I create a boson. How to do it? The way to do it would be the following. You simply write down S and Z is S minus AN dagger AN. You introduce a creation and annihilation operators for bosonic modes, auxiliary bosons, not realistic, just you brought it from the sky. It's the way you parameterize your spin, the way you describe it. Right? So in other words, immediately when you write down, you say, okay, I have my algebra, AM dagger is delta M, and of course AM is 0. This is the standard algebra, bosonic algebra. Yeah?
When you write the example code.
What?
When you write the example code.
I should not write here?
Yeah.
No, they fixed the camera.
Yeah.
Rotated just.
No, he told us.
Okay. You can write.
There is a suspicion, which means that 50% yes, 50 no.
No, the maintenance guy told us that.
He said?
Yes.
Okay. All right. Well, I was wondering why this is just created. All right. see every time I create a boson, the number of bosons here tells me what is the deviation of the spin from this maximum value. Right? There is a fundamental question here. Immediately appears, immediately arises. We are dealing with the spin operators. Dimensionality of the corresponding Hilbert space is 2s plus 1. Why? Because when I solve the equation, the Schrödinger equation for the z component of the spin, I find 2s plus 1 eigenvalues of the z component of the spin operator, which constitute the basis of my Hilbert space. My S is very large, so the space dimensionality is also rather large, but it's nevertheless it's finite. On the other hand, if I'm looking at the bosons, the particle number operator n, which is a dagger a, I can put I as a lattice side if you wish. At each lattice side, I have my Fock space, as I would say. And for the case for bosons, the eigenfunction I solve, right? N is equal to n. This n takes values 0, 1, 2, and so forth. Infinity. A countable number, but arbitrarily large number are allowed. Which means that the dimensionality of the Fock space emerging here is infinite. How can physics describe why a finite dimensional Hilbert space be equivalent to some other physics with the infinite dimensional Fock space? It's incompatible, right? So you cannot bring to one correspond. You cannot project one to another in the single valued manner. Of course, it's impossible, and there is no such thing like one-to-one correspondence. This correspondence is approximate, and it's based on the fact that looking at this picture, it's only a few arrows, if you wish, or a finite number, effectively, a finite number of deviations will be taken into account. Because of the restriction of the spin always remains large. Even in case you have some deviations, even the excited spin, the deviated spin, the reduced spin, the degree of its reduction is very, very small. So therefore, we are very close to the top of this picture. The deviations are small, so we do not explore the whole Hilbert space of the spin operator, neither do we explore the whole Fock space in the bosonic operators. In both cases, we are very, very close to the highest rate states or close to the vacuum states. So we can immediately conclude that, in fact, we need to deal with the low density gas of these excitations and try to keep certain accuracy. Now, to do a little bit more than what is written here, I have to introduce the expression for the lowering operator. Because if I act by S and minus on the ground state, that will give me a state with proportionality coefficient as until I reach the point n, let it be the site n, at site n I have s minus 1, and again s, and so forth. This is the picture. Acting on this state, on the vacuum state, S minus, reduces the spin by 1 at the point n, which is indicated here. So in other words, I have to create one boson at this latest site, right? According to one. So then let's be therefore write down something like it should be A and W. But then a very simple estimation shows that you have to put the square root of 2s in front. Of course, by arithmeticity, you'll write down as in plus s2s san, annihilation operator. And all this construction, this and this and this, are varied with this happens. Now, this is more or less fine. This is more or less fine. In fact, what is written here, it's an infinite series, which contains then terms like a dagger a divided by s, higher order terms, and so forth. Yes? Yes.
So the lowering Sn minus is proportional to the creation?
Yes, it is S minus is proportional to creation and not annihilation, because S minus decreases the spin, and every time you decrease the spin, you create a boson. You see? You create. Once you create the boson, there should be a creation operator. Yeah. So what you can do, and I suggest you to do it, as a home exercise, using this algebra of the E operator, you check the algebra of the spin operator. You cannot exactly reproduce it, because this relationship is not exact. It should be understood, it should be understood as an expansion in this small parameter. So 1 over s is our basic parameters of the expansion. The zero order term, it's not exactly zero order term. We immediately see what is the order of the ground state energy. So the excitation energy of the system should be proportional to the first power of s. And the terms proportional to of the order of 1 will be thrown out systematically. That's the essence of the Ostend method. We'll see how it works just right now. Let us plug these expressions, these expressions into the Hamiltonian that we have here. So what we have is the following: it is minus 1/2 J sum over n over G. Here we have S minus A dagger A n, S minus A n plus G dagger n plus G. This coming out from this. I use that. Then I use the expressions of the raising and lowering operators. Square root of 2s squared gives me 2s, 2 cancels 2, so I have s here. And here I have an plus g, dagger plus admission conjugate. Right? Of course, here I ignore all those corrections which I didn't write, but I will ignore even more than that. What I will keep here in this expression will be the first term that gives me s squared. The second term will give me s times an dagger an plus g dagger an plus g. So what I observe, the first term, of course, will give me the ground state energy. Right? The second term is proportional to the first power of s. It gives me a quadratic form of these bosons. So these are already excitations. And the lowest order they emerge is S. Right? And the same I have here. This I will keep. But I will drop the terms plus an dagger an plus g, dagger an plus g. This I will drop. Because I keep S squared terms, I keep the next order terms, I drop the terms which they describe interactions between the bosons. Good. Well, then what I obtain is the following. Our Hamiltonian is the ground state energy of a ferromagnet plus the Hamiltonian describing excitations. And the Hamiltonian describing excitations looks as follows. It gives me, this term, by the way, please notice that like it's sufficient to write down this term only and multiply it by 2. Because after the shift of A by N minus G, you will reduce this to that. So it will give me therefore J sum over N over G S, I have to put it somewhere, the first power sum over N over G. Okay. And here I have A and dagger A N. And here I have with the minus sign. By the way, the same story here. These things are double. But first of all, I can write them down as A N plus G dagger A N plus A N dagger N plus G. The sides are different, therefore the operators commute. And then I can shift N here by N minus G and reduce this to A N dagger A N minus G, but the minus G is a member of the same family, same G family as G itself. Minus G is a part of Nersesyan. So therefore summing over G or summing over minus G doesn't matter. So therefore it is simply minus A dagger A N plus G. This is the structure of the excitation Hamiltonian. Yes, right. So let me rewrite it in a slightly more elegant form, more suggestive form. The Hamiltonian of the elementary excitations looks like J S summation over G of 1 gives me Z, which is the number of, which is the coordinate and the coordination number. And I will rewrite this as sum over N. I will write down A N dagger A N minus 1 over Z and sum over G A N dagger A N plus G. This is a better form to deal with. So again, the ground state energy is the quantity of the S squared order. The excitation energy, as follows from here, is the quantity of all S order. Dropped, ignored terms, or 1 or even less. That's the structure of the theory. So you see that the ratio of excitation energy over the ground state energy is the small number 1 over S. The excitations are completely due to quantum effects. So therefore, we are taking quantum effects into account with this accuracy. That's the approach. Every time you do some kind of approximation, you have to have small parameters. And you have to take into account all the terms of the same accuracy. And systematically drop all the others, which are higher. Without justification, your approach wouldn't be good. Well, this is the way the theory looks. This term is pretty innocent. It's diagonal. It doesn't describe much physics, so to speak, even though it plays a very important role. But this is the amazing and most important term. It is not local. It's not diagonal in real space. And it cannot be diagonal. Because of the fact that first you create a particle at site N by annihilating on the nearest neighbor, that means that your spin flip starts moving in real space. So delocalization is here. The quasi-particle appearance is ensured. But now you want to diagonalize this model. That's a trivial task. The reason of its triviality stems from the fact that it's the simplest form possible. It's a quadratic form. Quadratic forms are all immediately diagonalized by the simple unitary transformations, which are Fourier transformations. So we expand, therefore, our operators in Fourier series square root of n, sum over all k, k belongs to the brilliant zone. You remember how it was? The k belongs to the brilliant zone. The brilliant zone is defined as, in three-dimensional case, a hypercube. It's a cube defined as follows. I don't need to explain it, as you know this. Here is the Fourier transform of your operator and the exponent. When I write down this n, it means that I write down Rn. It's abbreviation. Instead of writing down this, which would be sum over alpha, n alpha, and a alpha. A alpha would be just the basic vectors of the lattice, and n alpha would be just the set of integers. Positive, negative, including 0. Right. But you can immediately check that once we know the algebra of the bosonic operators in real space, the same algebra in K space follows it. So what we are left with is just we have to plug in this expression into what we have. Sum over n, a n dagger a n. Should we really plug this expression into here to anticipate the result, or can we write it down without any hesitation and without any calculation? Who can tell me the answer? I repeat my question again. I have the summation of this form, diagonal in n, summing over all n. I would like to see its expression in momentum representation. For that, I can, and I should, plug in this and use some rule. Do I really need to do all this calculation, or I can simply anticipate the answer, what the answer should look like? And why? This is a kind of the way to find out to what extent you are a devoted theoretical physicist. What is this transformation? What kind of transformation is it? It's a unitary transformation. What is the main property of a unitary transformation? Conservation of particle number. Imagine that you have an object, psi I, which can be represented as a column, psi 1, psi 2, and so forth. These are the components, psi m. Right? And you also have its conjugate, which can be represented as a line. And now you want to take a trace, psi dagger psi. It will give you psi 1 dagger psi 1 plus psi 2 dagger psi 2, and so forth and so on. Psi m dagger psi m, or in an abbreviated form, it's summation over all I psi I dagger psi I. Right? Now, imagine that you introduced a new transformation, a U transformation from psi to phi, following this prescription. When U is a unitary matrix, unitary, which means that U dagger U is 1, as well as U dagger is also. So, which means that sum over Ku Ki conjugate U Kj is delta Ij. That's what the unitarity means. Okay. If you now build out phi dagger phi, you will find out the following thing. You will find out this is psi dagger. This is U dagger or U minus 1 times U times psi. I don't write it in the matrix form, but I leave it to you. The structure is this. There will be an object intruding inside, which is U minus 1, but it's 1. It's identity. And therefore, it is psi dagger psi. And that's the main property. It's the length in some metric space. You can think of n-dimensional metric space. And the object trace psi dagger psi is the length in that metric space. And the unitary transformation is not supposed to change lengths. And the norms of the vectors on the lengths of some space should be intact, as well as angles. That's the main property of the unitary transformation. Therefore, without any hesitation, without any calculation, I immediately write down that this is sum over k, a k dagger a k. I simply change the notation. I move from n space to k space because the unitary transformation connects real space with momentum space. But the expression should be just the same. Because the length here and there should be the same. It's very important. It's something which you have to develop a kind of mnemonic memory of that. Every time you're dealing with the unitary transformation, of which the Fourier transformation is just an example. It's only one of those. There are many other unitary transformations. This will follow. Anything unclear? Anything? All right. But what concerns the second object, it needs to be indeed truly calculated. So I need to calculate now n, 1 over z, n and g, a n dagger a n plus g, 1 over z, 1 over n, double sum k k prime, a k dagger a k prime, sum over n, sum over g, exponent I n from here, minus k plus k prime and one more exponent, I k prime dot g. Correct? Correct. Now 1 over n, the summation by n of this exponent will gives me a chronic. 1 over n, 1 over the lattice number, summation of all lattice sides. I n minus k plus k prime, it's a chronic. It's a sum rule. Lattice, the famous lattice sum rule, you should have seen it many, many times in the theory of band theory of solids, lattice vibrations, whatever. So therefore, it transforms to 1 over z, 1 summation over k is removed, ak dagger ak, and then you have summation over g, an exponent I kg. So, from which you conclude that, let's start moving here, that the Hamiltonian of excitations is J, S, Z, double sum K, double sum K, AK dagger AK multiplied by. Now, the first term gives me nothing, gives me just 1. The second term gives me minus 1 over Z, okay, and now summation over all G. This is small. Which I will rewrite as follows. I will rewrite this exponent. This is a Hamiltonian in the following form. This summation of k, epsilon of k, ak dagger k, where epsilon of k is J S 2D one minus D summation over mu from 1 to D and cosine A mu A naught. Yeah, that's right. That's the way it looks like. Because when estimating the sum, I took into account that J is equal to plus minus A1, plus minus A2. Plugging in for each direction, plus and minus gives me twice cosine, and Z is 2D. 2 cancels 2. What remains is 1 over D, and the sum of the cosines. And that's the expression. Whether you like it or not, that's the expression. Let me only do one thing. Let me consider the limit when k is small as compared to the linear size of the Brillouin zone, small k limit. Then I can expand this cosine, and I will write down 1 minus k mu squared A naught squared divided by 2 instead of this. Now the term 1, summation over D will give me D, D will cancel D, this D, and 1 minus 1 will give me 0. What remains in this business is 1 over D. 2 comes out from here. A naught squared is here. And K squared. So, in the limit when K goes to 0, epsilon K goes to dk squared when d is 2d cancels 3d, j as j the spin a naught squared, nothing else. A naught squared. That's it. So, we have arrived at the, I would say, a spectacular result, which tells us the, first of all, we have diagonalized the whole time. The excitation energy represents a set of harmonic oscillators with the only condition. Can you see the condition? What makes this Hamiltonian special? When I'm saying that this looks like a Hamiltonian of harmonic oscillators, is it indeed a set of harmonic oscillators, or is some difference? Don't you remember we said that the ground state of a ferromagnet is classical, right? What would happen if I had said the ground state of an oscillator is classical? Then the oscillator would be immobile, like just at the bottom of the potential well, which is not the case. So there is a difference. How it shows up, if there's up. What is missing here? What is missing here? Plus 1/2. There is no plus 1/2. That's exactly because the ground state of a ferromagnet is classical. There is no zero-point motion. There is no uncertainty principle in the ground state. Nothing. In a ferromagnet, such thing doesn't exist. Yeah.
And also in this excitation we have this closed form because at the very first we ignore the interactions, right?
You mean the terms which have been dropped?
Yes.
Well, we dropped the term, that's correct. But before we start thinking about them, it's good to think how the free theory looks like. In the absence of this interaction will have an amplitude which is small. Therefore, I can think that if I first build up an ideal gas of such bosons, let me first find out the dynamics and the spectrum, and then I may try to calculate the corrections originating from that interaction. That's important in principle, but it's the next step. It's the next correction, or in the expansion of 1 over S. So in the main accuracy of the 1 over S, this is the end of the story. We have a set of free bosons. These bosons are very much like phonons, like acoustic phonons. In which respect they are the same. The chemical potential is 0 again, because the number is not dependent. It's not defined by the structure of this by the structure of the theory itself. You have to put your system into a thermostat or into a thermal bath, and then the temperature itself will determine the value of your phonons or of your bosons or your spin wave excitations, exactly in the same way as the Bose distribution function would determine the average number of phonons at a given temperature. The same is here, absolutely here. But there is one difference. The 0-point motion was the effect which would ruin the periodic structures in one dimension, as we have seen. Quantum fluctuations completely destroy long-range order, crystalline long-range order in one spatial dimension. It is not like this here because of the absence of the 0-point motion at all. It is not present. This is all you have, but nevertheless the chemical potential is still 0. So the lesson we have learned here is that in the lowest order in quantum effects, what we did, we took into account quantum effects in the lowest order possible. And in that order, the quantum effects show up, lead to a picture of excitations representing an ideal Bose gas. With the energy dependent on K, according to the small, you can build up this energy. It starts with a quadratic dispersion, then it curves and saturates out. It's absolutely clear there is a maximal energy. Moreover, this energy, as in any or any lattice, would satisfy the condition A K plus G would be absolute K, where G is the reciprocal lattice vector, the periodicity would be present, just the same stuff as before. The lattice shows up itself in the standard way possible. The good thing is to ask why the excitation energy itself, why the frequency itself is proportional to K squared, and not omega squared is proportional to K squared. Why is that so? Well, I answered this question last time. This is because time reversal is broken. Breakdown of time reversal follows from the very fact that the spins get ordered. There is a finite magnetization in the system. That means that there is a huge current, if you wish, electronical current, which creates each moment. So you can imagine the coherent effect of these currents. Every time you fix the direction of this current in the perpendicular direction, you will get a magnetic moment. You change the direction of rotation of your electrons, the magnetization will be overturned. So every time magnetic order or non-zero value of magnetization breaks time reversal. Because of that, we don't have any serious reason to get omega squared in the dynamics of our system. So this will be just actually the problem we are left with, and we'll turn now to that problem to understand better what these elementary excitations mean at all. What do they carry? What quantum numbers they carry? Well, the quantum numbers is more or less fine. We overturn the spin, and the overturned spin is always excited spin is 1, and then it gets delocalized. So therefore, the elementary excitations carries the spin 1. This is for sure. But how it comes about? What is the spin wave? What is the physical quantity which undergoes some kind of oscillation, right? So there is an equivalent approach, absolutely equivalent to what we have done. Maybe first of all you have questions here. Just ask me now. Okay, so I'm going to erase basically what we only have. Is there anything unclear? No. All right. So before we turn to the understanding of the meaning of magnetic excitation, such as spin waves, let us recall the old problem of spin dynamics in an external magnetic field. Just you have an isolated spin, only one, localized at some point in space, say at some lattice site. There are no other spins, but there is a magnetic field applied to the spins. So we're talking about the Zeeman effect, as you should remember in quantum mechanics. And the Zeeman energy is geomagnetic ratio, Bohr's magneton, the magnetic field H times the spin operator. This is the energy of your system. Let us specify the direction of the field. Let H take value, let it be 0, 0, H. And therefore, let me introduce then omega naught such a frequency, which is defined as G goes magneton and H, and then it will be minus omega naught at Z. So I've chosen the direction of the magnetic field to be the quantization axis for the spin. I quantize the spin along the direction of magnetic field. And of course, the eigenvalue of the energy is parameterized by the number m. It's omega naught m. When m takes values minus s plus 1, and so forth and so on. The rest you know. It's the standard splitting of the energy levels of the magnetic, of the spin and the magnetic field. Zeeman split. Now, at this point, let us play the following game. First of all, I would like to ask you, do you know what the equations of motion are in quantum mechanics? If you have operators in the Heisenberg representation, do you know that? Do you know the importance of those equations? So it's again silence, basically silence. All right. Suppose you have a Hamiltonian, just a Hamiltonian, and you have an operator A, which is an operator in the Schrödinger representation, and you want to pass from Schrödinger representation to Heisenberg representation. What do? You forget about the fact that the wave functions were time dependent and operators were not. Now everything is another way around. The operators will become time dependent, whereas the state vector will be not. So the time dependence of the operator is defined as I, H, T, A. This is the Schrödinger operator, minus I, H, T. So in fact, I would have to divide by H by the Planck's constant, but I prefer to work in units when H is 1. Right. Now let's look at the equation of motion of this operator. I, time derivative, AT. It immediately follows that it's a commutator of AT with the Hamiltonian. We differentiate it once here, we differentiate it second time here. The signs are different, they organize themselves in the commutator, and that's what you have. Just an equation. If you are able not only to calculate this commutator, but to calculate all the commutators for all emerging operators, because if you calculate this, if you do this calculation for this commutator, the right-hand side would not only contain AT, but some other operators as well. So now you will have to write down new equations for new operators. And the process will continue. And generally speaking, it will not be stopped anywhere. Now there are special cases when the problem is getting very, very simple. Namely, that's the case when your Hamiltonian describes is diagonal and it's one particle. So let A nu be creation A nu and A nu dagger, annihilation and creation operators, with nu being a quantum number. And the operators may be either Fermi or Bose, it doesn't matter what. Statistics is unimportant. For this operator H, you may ask yourself how this equation looks like. How does it look like? So I introduce the Heisenberg representation for the annihilation operator exactly in the same way as a prescription requires. And then I have to calculate everything in the following way. It will be IHT and the commutator A nu and the Hamiltonian. And again this. But now this is trivial. This commutator, for whatever the statistics is always absolute nu and nu. Full stop and nothing else. which means that A nu dot T is minus imaginary I, epsilon nu, A nu T, which means that the solution of this equation is the Schrödinger operator, so to speak, minus I epsilon nu divided by T. If you are very pedantic, you will write down Reinstall the Planck's constant. So it looks like very much what we write down in the Schrödinger picture when we built up a time-dependent wave function for a stationary state. For a stationary state, the time-dependent wave function for the solution of this equation looks like minus I, energy level, T, and H. This is how the time-dependent, the solution of time-dependent Schrödinger equation looks like. And here is the solution of the equation of motion for the annihilation operator, second quantized operator, but for free particles, for a free particle. You see, in fact, the statistic cannot play a role because the statistics start playing a role when the particles correlate, interact. There are many particles and there is some kind of correlation between them. The particles are free. Well, there is correlations even at the level of free particles, but when I consider a single particle dynamics, it cannot be dependent on the statistics. Only a system of identical particles can depend on the statistics. So therefore we can say that the solving the Schrödinger equation or writing down the equation of motion for the operators is just the same job. It's a matter of taste, not a big advantage. The problem emerges not at this level. The problem emerges when a part of this Hamiltonian, you have something like this, for instance, sum over nu1, so a fourth, nu4, some coupling constant u, nu1 and so forth, nu4, a nu1 dagger, a nu2 dagger, a nu3, a nu4 with some conservation law imposed on this nu1, nu2, nu3. For instance, if these are in momenta, then the total momentum gets sure. So you have four operators now. If you calculate the commutator will kill 1 degree of A dagger and give you just A for pre-particle. But if you have a term which contains four operators, this operator A, when calculating the commutator with a quartic term, will kill this one and leave you with this one. In other words, if you write down A dagger, A dot, it will reduce to A dot, and also you will have something like A, what is it? A dagger, A. I don't write the corresponding suppose. 1, 1, 1, 2, 3, then you will go have terms more. 3, 4, dagger, 5, and so forth and so forth. This is what you will get. And then if you started with the equation of motion for the first order operator, then you will have to turn to this operator, and that will express again in terms of all the others. It will be infinite set of equation, and you will be lost. You throw out all your job into the basket and go back home or play snooker or something else. Or go to the pool and start swimming. But physics is over. What to do? What to do is just to invent a reliable, approximate scheme. You cannot move otherwise. You have to invent an approximation. If you are lucky enough, and if you have a well-defined small parameter at your disposal, the control parameter, I would say, then you can try to do some kind of job. We have the same situation for a semi-classical description of a ferromagnet, and we will use the fact that we have a well-defined scheme, which is 1 over S expansion. But let us first try to find out what do we get from a problem like this, which ends up here. Because our problem, this problem, is of this class. It's closed. It can be solved exactly. And everyone knows what this is. It's a precession of the spin around the direction of the magnetic. I have a few minutes. Let me go fast. I will remove this and this. So, good. The first thing I would like to do is to write down the equation of motion for the z component of the spin operator. And the z component of the spin operator as a function of t should be the commutator of sz of t will be Hamiltonian, which is minus omega naught exponent as z and in the commutator we have the sigma operator, which means that the right hand side is there, which is trivial because if there is a magnetic field, the projection of the spin on the direction of the magnetic field must be conserved. So there is no time dependence of the z component. That component is a good quantum number. But now what you can do is to build up this equation. And I remind you that this plus is Sx plus I is y. It will give us minus omega naught, again, this exponent. Let me plug in as x plus I as y, z, and again. What is this? This commutator, according to the SU2 algebra, is minus I as y. This is I, and again I have I as x, but I times I gives me minus. Altogether it gives me minus s plus. So I s plus dot is omega naught s plus time s plus dot t is minus I omega naught s plus t. So therefore s plus t is the initial value of this operator minus I omega naught t. As simple as that. Right? So my immediate reaction is, when you get used to a calculation like this, and do them at least once a week, then the first thing I want to say, look, this is a manifestation of the fact that the two-dimensional rotation on the unitary group U1 is just the same. Multiplication in complex analysis, the presence of this exponent is the same as in real space, in real two-dimensional space, you will get a rotation. In other words, if you now use this definition, you will find out that Sxt, that will be Sx naught cosine omega naught t plus Sy sine omega naught t, and I don't want to write down what is Sy, it's just a two-dimensional rotation by an angle omega naught t. So that's the picture of the physical picture which emerges in this case. So this is the direction of the magnetic field, which is the z direction. This is the z direction. This is the instant instant value of the spin, if I had looked at it quasi-classical, that would be the Z projection, which doesn't evolve at all. It's a fixed, it's a conserved quantity. And then you put down the projection, and then you have this rotation of the transverse component of your spin in the perpendicular plane. In other words, your spin as a whole goes classically or semi-classically along the surface of this cone, and this motion is called precession. Right? Quantum mechanics actually gives us a semi-classically meaningful result. It tells us that Sz is conserved, and the transverse component of the spins undergo a precession. But by the spins we mean operators. Then you can build a state, act on these operators, and find the dynamics of the state already now in the Schrödinger picture. So this picture is good because it allows you to work out the time dependence of the spin operators. When you know the spin operators and you know the initial wave function, you act by those time dependent operators on this wave function, you find out the time dependent wave function. So you go back to the Schrödinger picture. It's very simple. The message is, for a spin, for an isolated spin, in a magnetic field, all you find, all dynamics, is simply a precession. Now, if you have many spins in the same field, in the same magnetic field, of course, the final picture will depend on the initial phases of the spins. Right? But assuming that all the phases are coherent in the very moment, then you have the overall precession of the total magnetization around the direction of the field. The field will define everything, the frequency of the rotation and whatever. The good question would be to ask, what is the difference between this picture of isolated spins and the interacting spins in a ferromagnet? This is what we will do next time. And then we will finish that time, that problem. We will turn to the much more interesting problem of antiferromagnetic.